Hey, my name is Charlene Teachout.
My name's Levi Winkles.
I'm Austin Posey.
And I'm Austin Hoff.
And our project is on floating point addition. The name of our research paper is a software implementation of the IEEE 754R decimal floating point arithmetic using the binary encoding format. This was originally created for financial purposes, but for our project we only implemented the addition part. So basically a simplified explanation of this is that you have a floating point number and a slightly smaller floating point number, and what the algorithm will do is it will truncate these two numbers and then add them together, and then the appropriate number of zeros is added back on to give you your final solution.
All right, so the code is written in C++. I just followed the algorithm that was given in the paper. You'll notice that there's a bunch of different functions here, and they all do something different. But the function digits here returns the number of digits that would be lost due to the truncation, and so that's kind of an important number because we need it for later. But the algorithm itself accounts for overflow and underflow, so that's a neat thing that it does, and it does so at the end here. It also rounds to the nearest even, which is done, I believe, right there. Up top here, you'll notice that we have a constant called p. This is an important number as it signifies the number of significant digits that we want to keep. So we can change this to whatever number that we want. We just left it at 4 to make things simple. Otherwise, if the numbers get too big, it can be a little bit messy. The algorithm itself it allowed for inexact numbers somewhere in here. Like they gave you 2 different options that you could do, but we opted to do the exact numbers because we weren't for sure what the reason was for inexact numbers and why you would want something that was inexact. But the function itself is pretty simple. It just checks the exponents to make sure that they're similar, and if they aren't, then it just returns the larger of the two. And if they are close in size, then it will just it will add the two that are truncated together, and then it'll add those two, and then if it needs to truncate, it will truncate again, and then it will round afterwards, and then it will return the value. And that is it for this.
All right, so we're going to test out our program here. Okay, so N1 is our first number and N2 is our second number. N1 is a couple digits longer than our first number. So what the program does is it takes, so in this case P was 4. So it truncates the last 3 ones off the first number and the last one off the second number. And you can see that in E1 and E2. So C1 is what it gets for the first number after it truncates it, and C2 is the second number. And then it adds those two together and then adds the 3 zeros back onto it, and that's how you get the result. And we can try a new number. So let's try that and recompile it. And yeah, in this case, yeah, E1 and E2 are the same. C2 is 2222, and then the answer is shown here.
To conclude, our code adds large floating point numbers and truncates any overflow. There are restraints with working on large floating point numbers. For instance, if you have a 32-bit or 64-bit operating system, you can't add 2 numbers larger than your operating system and store them. It's just not possible. And likewise, the summation of the 2 large numbers can't be greater than what your operating system can hold, 64 or 32-bit.